Thank you, Maziar. As you already said, we're going to talk today about performing dynamic analysis of structures with the DIANA program. In this webinar, I'm going to talk about 4 parts, split it into 4 parts. The first part is the introduction, what is dynamics, and some background in general. Then we go to the modeling aspects for dynamic analysis, and that is of course dedicated to the DIANA program. Then we have a special section on fluid structure interaction. This is actually also a modeling part, but because this involves specific information, specific elements, we go there into a little bit more detail. And we end our webinar today with an overview of the dynamic analysis types and their typical features and options you can use during these analyses. First, I would like to talk to you about the definition of dynamics. Then we go into the equations of motion. Then we show some examples of typical dynamic analysis. Dynamics. What is dynamics? This is coming from the internet, from Wikipedia, but this gives a short and good description of what dynamics is. Dynamics is a branch of physics concerned with the study of forces and their effect on motion. What is important here is that is the word forces, and in forces you also need to think about moments. It's not really say only forces, but also the moments and their effect on motion. So we have 2 typical things here. It's about forces, say the driving mechanisms to get an object in motion. And Isaac Newton, who defined several fundamental physical laws, also defined one which is actually the equation that is used in dynamics all the time. That is F is m times A, where F is the force vector, m is the mass matrix, and A is the acceleration, which says then that the forces applied on a mass or masses of a system will give them a certain acceleration. And we will see this also coming back in our equations of motions. Here we still have the term, I'll go to start with the generic one of course. We still have the term which we saw on the previous page. M is u the double dot, which means it's the displacement and then the second time derivative. So this is the acceleration term, which means that all other parts you see here should be the forces. That is correct. We have the external forces, we have internal forces, and we have some damping forces. We arrange this in a little bit different way so that on the right hand side we see our external forces only, and on the left side you see the inertia forces, the damping forces, and internal forces which may come from all kind of sources. When we go from the generic part to the linear form, then these internal forces can be written as K, which is the stiffness matrix, times a displacement field U at a certain time. While in case of a nonlinear analysis, these internal forces are the integral over B transpose times the sigma, the stress tensor over the volume. We will see these equations coming back several times during this presentation, and then we will go into more detail on the different terms you see here, which you can use for which kind of analysis, and how you can set up or give the required information to set up, for instance, a damping matrix or to set up the forces which will drive your dynamic analysis. Now we're going to show quickly some dynamic analysis that can be done with DIANA and are also often done. So we have earthquake, then we often talk about, say, a seismic analysis instead of a dynamic analysis, but it's just a specific form of a dynamic analysis. Then you can think about wind loads. For instance, if you have to design a building close to the sea where you have quite severe wind forces, and these wind waves or water waves, if you are working, say, offshore, will also act as a driving force on your structure. Another type is explosions. Here it is, say, the more of a very short type of loading, but it can result in, for instance, shock waves that are hit your buildings and get them into vibration. Further impact loads, traffic-induced vibrations, like you see here on the picture, a train going over a bridge, traffic on cars, trucks on a viaduct, and so on. Rotating machinery in factories, or also in you can think here about, say, hospitals, where your MRI or other dedicated equipment is positioned, and you want to make sure that these are not experiencing any vibrations in the building, because then it would make them not functioning correctly. Another one that we have recently done with one of our customers is, for instance, pile driving, where a pile is driven in the ground and one impact on the pile is being modeled to see how deep the pile drives into the soil. Now we are quite interested in what applications do you want to use dynamic analysis for, so we're going to have our first poll. Thanks for providing us this information. It's a quick overview. Most of the people are doing the dynamic analysis on buildings in general. There's a lot of people that are interested to do dynamic analysis on bridges. And what is also clear is that most of the people, or at least a large group, is interested in the interaction with the soil during dynamics. I tried during the rest of the presentation to point out a little bit more in detail on these fields where possible. So I would like now to continue to the second session, where we're going to talk about the specific modeling aspects. And in this part, we're going to talk about the wave speeds in structural elements. This is important because vibrations, the waves, travel with a certain speed through your model. And if you want to be able to view these waves correctly, you need to take into account some information, some details with respect, for instance, to your element size and the highest frequency you want to be able to see in your models. Further, as we already seen from the second law of Isaac Newton that dynamics is all about getting mass in motion. So how to define your mass in your system. Typically is also that you need to do something about damping. It's not necessary. You can also do undamped analysis, but in most cases you would like to add some damping to your model. The next thing we're going to talk about is loading, and I'm not going to talk about all the loading possibilities of DIANA, but only to the dynamic specific loading, which you're probably not going to use in, for instance, a linear static or a static nonlinear analysis. Further initial conditions can be important during dynamic analysis. For instance, your construction or your object may already have an initial velocity, or especially for buildings, bridges, dams, so on, you probably already have a pre-stressed situation, maybe already just from the dead weight load, and you probably want to include that in your dynamic analysis as well. Further, we're going to talk about the far field medium. Here you need to think about what will happen when these waves are traveling. In real life, these waves will travel on because they are normally not limited. But with a finite element model, you've already said it's finite. So there is somewhere a boundary on your model. And then you want to know what will happen to the waves when they reach these boundaries. And we go into detail in that in the last part of this section. First, we're going to talk a little bit more about the waves. What kind of waves do we have? We have compression waves, which will occur both in solid and in fluids. And there you see there is a sort of compaction in these regions. So this travels on. It's dilatating your soil, your medium, or your fluid. Then another one is shear waves. Shear waves are not occurring in fluids. They're only occurring in, say, solid kind of materials. These are normally, the compression waves are called the P waves. Also quite often mentioned, say, the primary waves. That is because the P waves are traveling faster than the shear waves or secondary waves. And this distance in wave speed is, for instance, being used for earthquakes to locate the epicenter of the earthquake. Because if you know the distance between the arrival of your P wave and your S wave, you know the distance from your source of the earthquake. And if you do that for several points, then you can localize the epicenter of the earthquake. It's not directly related to the finite element in this model in this case, but it shows a little bit where these waves are being used as well. In structural elements, we can calculate these wave speeds because they are related to the linear elastic properties of your material. In this little example here, I use a dense sand, well graded, SW categorization. Say for instance the Young's modulus of 200 megapascals and a Poisson's ratio of 0.35 and a density of 2000 kilogram per cubic meter will lead to a primary wave speed or the pressure wave speed of approximately 400 meters per second, and the secondary wave speed, the shear wave speed, is 190 meters per second. So as you see, the P waves, the pressure waves, are the fastest one, and the shear waves are the slower ones. This information we will use to learn something about an appropriate element size. Note that these are just an example for well-graded sand. In your model, of course, it's necessary to calculate it for your appropriate materials. How this is related to the element size. What we would like to see is if we would nicely want to see, say, one wave, say one sine wave, and we need at least, say, enough elements In this case, we say that 20 is a nice number to really represent the wave, the shape of one wavelength good. Of course, you can say maybe 15 is enough, or 10, or maybe you prefer 30. So you can always adapt this value here. But what you want to know is that for your shortest wavelength, you want to have enough elements to represent the shape of such a wave at a certain time correctly. Say, for instance, if you would have had only, say, 2 elements, then you would probably have seen something here probably around, say, 0.7, and somewhere here minus 0.7, but you never could see, you have not enough accuracy to nicely represent your wave. So if you're really interested in what's happening, for instance, in your soil, make sure that your element size is sufficiently small to show the shortest wavelengths. The shortest wavelengths will occur for the lowest wave speed, so the shear waves. And you probably also have a maximum frequency of interest in mind. Say, for instance, we go back to our well-graded sand, where we had 400 meters per second for the primary waves, and the slower shear wave was 192 meters per second. Say that our maximum frequency of interest will be around 50 Hertz. That will mean that this wavelength, which is just our our CS divided by Fmax, we will see that it is 3.8 meters. If we want to have, say, 20 elements to represent 3.8 meters, that means that our element size should be around 20 centimeters, 19 centimeters if you want to be precise. So you can also work around, of course, the other way around. If you have made already a mesh and you would think from, okay, it's nice, I don't want to adapt my mesh, but I'm quite interested what my maximum frequency that I can see well will be, then you can just do the calculation the other way around. You fill out your element size, you calculate your shortest wavelength based on your properties again, and then you can calculate what will be the maximum frequency that will be visual with your mesh. The next thing what we're going to talk about is about the mass specification. How do you get this mass into your models? For continuum elements, probably the largest part of your model is just the mass density that you're going to have to specify. The mass density is being used for the dynamic behavior. For some soil-related models where you want to do a buoyancy correction, you can have a second mass density, what is called reduced mass density, and that will be used only for the dead weight load. So in that case, you have to define both your mass density and a reduced mass density if you want to take the buoyancy correction of submerged media like soil into account. If you're just acting, for instance, with concrete or steel, you will only specify a mass density. The reduced mass density is typically for soil and other porous media. Next to the continuum elements, you maybe have dedicated mass in your model, which you can just represent by point elements. They contribute both to the dead weight and also to the dynamic behavior. You can even specify them direction dependent. So if you want to say that this amount of mass will only work in vertical direction, you can specify that by leaving your two horizontal directions 0. Another option is to use distributed mass elements. For instance, line elements for 2D models or surface elements for 3D models. You can use this, for example, as we can also see in a later example, where you have, say, for instance, a reinforced concrete building where there are some additional mass elements. You can think about furniture or equipment or machinery, and you're not really interested in the details of these elements that are placed on your reinforced concrete building, but the mass that is there is of course very important for the dynamic behavior, so you need to take that into account, and you can just place it on your structural elements, on your continuum elements, by adding some distributed mass elements. These will only be used in the dynamic behavior, so there is no dead weight contribution from these elements. Also, these elements can be defined in a direction dependent way, and there is a special application, a special mass distribution, which is the so-called Westergaard mass distribution, that will then be of interest for the people doing a dam analysis, because this is a typical mass distribution of the fluid acting on a vertical dam. So without doing a full fluid structure interaction, you still can account for the mass of the reservoir by applying distributed mass elements. Alternatively, as we will see later, you can do a full fluid structure interaction to calculate the mass distribution. The other thing that we have seen from the equation of motion is that in most cases there is damping in the system. We have several types of damping. The first one is the viscous damping, which is proportional to the velocity. That's also what we saw in this equation of motion, because it was C times the U with a dot, or so the C is the damping matrix and the U dot is the first derivative of the displacement, which is the velocity. In most cases, the Rayleigh damping is given as Rayleigh damping coefficients for structural elements, and this damping is built from a contribution of the mass matrix and the contribution of the stiffness matrix, as we will see in the next slide. Next to that, we have structural damping, which is proportional to the displacement. It's not dependent on any frequency, and this type of damping can only be applied in a direct frequency response analysis. And then we have a third type of damping, which is so-called continuous damping, and this is coming from the discrete spring Dashpot elements. So these you can use if you really have, like, your shock absorbers in your car, if you really have damping real dampers, physical dampers in your system. You can also think about these devices that you have on buildings, on top of the buildings or inside the buildings, that are actively damping out the earthquake motions. And for these parts, we advise you to use this discrete spring Dashpot elements with the appropriate damping values, which are normally provided from the component manufacturer. Further, you can also add continuous damping to the concentrated mass elements, which I showed in the previous slide. We want to go a little bit more in detail into this Rayleigh damping, because this is the most common form of damping being applied. As I already just said, the damping matrix is in this way set up as a fraction of your mass matrix times another fraction of your stiffness matrix. And how to get to this alpha and beta values? These are normally related to the amount of damping you want. This is these damping ratios here, the C1 and C2. And you have two angular velocities or two frequencies where you want to set your damping. So we have, say, frequency 1 here with a damping of 3%, and we have another frequency here, 25 Hz, with a damping of 5%. These 2 points define this curve. A Rayleigh damping curve always have two asymptotes. One is at 0 Hertz, say the static one, so it goes to infinity on this side, and the other one related to the stiffness is going to be a linear one starting from the origin and going in a diagonal way. And the Rayleigh curve is always fit between those two curves. If you use these formulas to find your damping ratios, you will always find out that your alpha and beta will have non-zero values and even always positive values. In case you want to set your alpha and beta yourself, make sure that you never add negative values, because it would mean that instead of that there is energy dissipated from your system, you are adding energy to your system, like you have an actuator in your system. It is possible, however, that alpha or beta is 0, but the nice thing is that there are several tools, and if you have these formulas, you can always quickly check what the damping is, so you always make sure that your damping ratio is never below 0. Here we're going to show you an example what we have had recently. In this case, from an organization for benchmark, there were 3 damping ratios provided. The first eigenfrequency had a damping ratio of 2.6%, the second one had a damping ratio of 4.2%, and the third one had a damping ratio of 5.5%. We have indicated these provided values with the 3 green dots in this graph. Because many people say when applying the Rayleigh damping, you need to take the first 2 eigenfrequencies or 2 eigenfrequencies. That is an option, but in this case we always say from next to these eigenfrequencies, it's always important also to know from in which range is your loading and in which range is your response of interest. So we wanted a little bit more, so we wanted to have a maximum of 5% damping in a frequency range of 0.5 to 15 Hertz. Of course, because of the first asymptote, we cannot say we want to have 5% at the 0 Hertz, which would maybe even be more preferable, but due to this asymptote it's not possible. So we say we started from a half a Hertz. This is done for a seismic analysis. But we also wanted to make sure that in our interesting frequency range from the loading, we know that our loading was limited by filtering to 30 Hertz. We wanted to make sure that we are not, say, over damping the load, the energy in the loading in the range of 15 to 30 Hertz. So we also want to make sure that we never exceeded the 10 Hertz in this range. And altogether, this gave us an alpha of 0.3, so it's the factor for the mass matrix, and a beta of 1,000 for the stiffness matrix contribution. And you see in that way we are close to the damping of the first and third eigenfrequency, and we have a little bit less damping for the second eigenfrequency than was measured, but over the entire frequency range, or 0 to 30 Hertz, and within the especially detailed range, or 0 to 15 Hertz, we have a nice damping distribution. So we were quite happy. So you see that it's in practice not always possible to match all your points or all your frequencies. You say I want to have 5% for every frequency between 0 and 10 Hertz. It's just not possible with Rayleigh damping. You need to keep that in mind, and by playing by these values you can also play with the shape of these Rayleigh damping. So you can also see that your damping is not going too low. So it is sometimes wise to spend some time on choosing the range until you have a Rayleigh damping graph in your frequency range of interest that is fulfilling your needs. So don't focus only on just 2 frequencies, but think about the entire range. What do you expect for your response? What is the frequency in your loading? And take all these things together while setting up a Rayleigh damping properties. In case of the discrete spring dashpot elements, as you can see, one here, this was one below a bridge deck to for a train. It's near the train station, so the trains are braking here, and which will cause some vibrations to the viaduct. And these dampers are used to damp out these vibrations. In DIANA, you have both translation or rotational spring dashpots. These can be 1 or 2 node elements. In a 1 node element, this one side is always connected to the fixed world, so it is fully supported, and the second node can be connected to your structure, or the other way around. If you have 2 nodes, of course, then this part of the structure is here and another part of the structure is on this side. You can, next to the spring stiffness K, you can also provide the damping coefficient C, which may be frequency dependent for some kind of analysis, if we can see later. These spring dashpots can have initial stresses, and they can have a working direction. By default, for a 2-noded element, the working direction is from node 1 to node 2, unless you specify another direction. For instance, if you want to work this spring, say in a vertical way, something like this, then you can give a direction in Y or in Z instead of using the direction from node 1 to node 2. On this slide, I provide you some damping ratios, damping percentages, as provided in the book for Dynamic of Structures from Professor Chopra. And you see, depending on your material, when we go, say, from welded steel, which has very less damping, to wooden structures, which have 5 to 7% of damping, when you're just not very heavily loaded. When they are near the yielding point, you see that for steel, your damping goes up to 5 to 7%, but for wooden structures, it can even go up to 20%. And of course, for many of our users, the range here with the reinforced concrete and pre-stressed concrete is of interest, and you see, depending on the loading, it will be between 2 to 3 and 10%. So quite often 3 to 5% is used as a starting point, but may be adapted due to specific needs or specific loading conditions. Now we nicely come to the next slide, where we're going to talk more about the loading. As many of the people here are interested in the seismic analysis, we want to apply the earthquake. And in DIANA, we have 2 ways to do that. The simplest way is a base excitation load. This is a translational acceleration in a specified direction. And it will work at all supports which are supported in the working direction. So for instance, if you have an amount, your soil, and at the bottom you want to apply a horizontal base excitation in X direction, you specify the value for your acceleration, you specify your working direction X, and it will automatically be supplied to all the supports in X directions. You can have up to 3 orthogonal directions, so X, Y, Z, most logical, but any direction system, as long as it's orthogonal, can be used. But for long constructions like bridges, it is not always wanted that on all supports, say on all these piers here, the acceleration, the earthquake starts at the same time, because this earthquake has a traveling time. In that way, we can use prescribed accelerations. These can be translational or rotational. Also, these have a working direction, and you can then apply them to a set of nodes. And then when attached to time curves, if you can see later, you can make sure that, say, for instance, on this left side, the earthquake will slightly start earlier than on the right side. In this way, you can, for large constructions, you can take this effect into account. While base excitation would say this entire bridge is going to shake all with the same motion at the same time with the prescribed accelerations and dedicated time load curves, you can make sure that there is a time delay in when the earthquake arrives at each pier. It's also depending on your model what is most applicable. What already said that you can connect these base excitation loads or these prescribed acceleration loads to so-called time load diagrams. This is just a load factor to the acceleration specified in your base load or in your prescribed acceleration. In this way, you can generate the accelegrams as you are known in seismic analysis. So you have two horizontal ones and you have one vertical one. So you just gave your acceleration. What you can do, for instance, set your base excitation by default to 1 meter per second square, and your time load diagram is then directly your accelerogram. Or if your accelerogram provided for measurements is, for instance, in centimeters per second square, and you choose your acceleration to 0.01 meter, then you directly have your accelerations in meters per second square. Or you want to use G as, so you have many possibilities. It's not set you always need to do your base acceleration as 1 and your accelerogram as loading. It's just that the product of your load and your time load diagram is the actual loading at that time point. There can be multiple diagrams, as already said, say for instance for an earthquake, 2 horizontal ones and a vertical one. And the applications will look up, say for time 4, it will look up for X, my factor is minus 0.2. My factor for the Y load is, say, 0.1. And for the vertical, it is, say, for instance, 0 at the same time. And the application will make sure that each load is applied correctly at the same time. So it's nothing you have to combine. You just give up your individual directions. Yeah, so you have 3 loads with 3 time load diagrams, and you can do a full 3D transient dynamic analysis. When you want to calculate in the frequency domain, then we have something similar. This is a frequency load amplitude diagram. Then in this case, your multiplication factor is on the vertical one, and instead of the time, we use the frequency scale on the horizontal one. Also here, these diagrams can be input as directly, so you give your frequency and your factors 0, 0.5, say 1, 2.7, 3, 2.7, and here you can split it into several points to represent this curved part. It's also possible to use external file. That's also possible for the time load diagrams. So then that way you can easily just use an accelerogram. It's possible with this frequency load diagrams also to introduce complex loads, because you can give either the amplitude and the phase as a function of the frequency, or you give the real and the imaginary part as a function of frequency, which can be of interest if you have, for instance, multiple loads in machinery and you have a phase difference between the forces. For seismic analysis, according to Eurocode 8, you can also let DIANA generate the elastic response spectrum and the design spectrum based on the soil properties and the region as specified in Eurocode 8. Also here is that multiple diagrams are allowed, and the application will check all the diagrams related to the loading, how much of that load will be applied at that frequency. Next thing, what's still interesting in the modeling part are the initial conditions. This can be initial displacements or velocity, translational, rotational. You can apply them at the nodes. You can also calculate initial displacement from a linear static analysis. You can use pre-stress loads as initial condition. You can also calculate your initial stresses from a linear static load, or you can take up the current stress state from previous loads that in, for instance, in a combination with static analysis. So in case you first are going to build your bridge, so you have your stresses from the construction process or your dam, or you want to take into account certain temperature conditions which yield to a specific stress state, you can use that as a starting point for your dynamic analysis. When we come to the far field, I already told a little bit in the beginning. What you normally have, your model is limited. You cannot model the entire world, and so you need to make assumptions on what will happen at your boundaries of your model. What normally will happen if you do nothing special is that when a wave is traveling downward and there is just a normal support here, the wave will be reflected and will travel up again and will remain in your model. This is probably not what you wanted, because in reality a wave that is somewhere started will go on and will move out of your model. In that case, you can model this boundary in a specific way, what we called a far field boundary. That way we use some viscous dampers. In this case, they are modeled with interface elements to have a nice distributed properties, which makes it easier. Unless you have a very regular nodal distribution at your boundaries, you could also use, of course, spring dashpot elements, but in that way you probably have to set the properties for each spring dashpot combination individually, which makes, of course, a lot of work for large models. These damping properties are also working for the compression waves and shear waves, and they have also specific properties for the direction that the wave is coming. So for the pressure waves, so the stiffness in the spring direction, you will provide your CP value for the damper, and in the shear direction you will provide the CS. And you can see these damping coefficients are again related to the material properties, and they can easily be calculated from your medium here. What's more interesting here to say that you give a certain distance here to the far field, you give your directions and the configuration, and you give the mass density of the far field. So in case that, say, your sand is here connected to a more rock type material, you can adjust that here in the mass density for the far field medium. How is this working? Here we have a very simple example. Here we have a soil column with a far field medium. So what you actually model in DIANA is the soil column and these dampers, and you stop more or less here, because here you give the distance of the far field. So you're not modeling this with physical elements. No, you model it here with these boundary elements, which you give a distance, you give the property of this soil. And what will happen if you get an impact here on the right on this soil column? The impact hits and you will get some movement here of this soil column, and you will see that it remains around -3 in this example, -3 e -2. So let's say 3 centimeters, for example, that it is pushed down. What would have happened if we had placed here conventional supports? In that way, we also go down to -3, but at that time, the wave is traveling back, resulting that this part keeps vibrating, especially in this example where there is no damping at all. Then you have an impact, and what will happen is that the soil will keep going up and down, while in real life the wave should have gone into the far field and gone away. The question whether you need these far field boundaries is dependent on a lot of things. It is some extra work to put them in, and if you don't need them, there's also no need to do it. When do you need them? For example, if the time you're going to calculate, if with the wave speed, if during the analysis you're not going to hit your boundary, there is also no need to add a reflective or non-reflective boundary condition, because your wave will not be there at the end of your calculation. Or in cases you have high damping and your the wave, when it reaches your boundaries, is almost damped out, then there is also no specific need to do a far field boundary. But in case you have not so much damping, you have high wave speeds, and you want, for instance, to do a full seismic analysis of 20 or 30 seconds, yeah, you're going to need to do something at these boundaries to avoid that the energy keeps into the system and is reflecting and giving you inappropriate dynamic behavior, because you see a lot of things which are physically not there, but due to your modeling and without non-reflective boundary conditions, yeah, you will end up with maybe way too high stresses and cracks in your construction, which may not occur in real life. So it is important to think about this and to decide based on some calculations whether you need those non-reflective boundary conditions or not. If you're in doubt, I would say use non-reflective boundary conditions, and only in specific cases where you know that there is no need to have them, then avoid them. But if you want to play it safe, just use them. We have the tools for it, so make sure you have them. Now we come to the fluid structure interaction part. It's probably especially of interest of the people doing dam analysis, as you can also see here in the example. I will tell a little bit about the assumptions and the limitations of this kind of fluid structure interaction. Going to tell about the domains and the different boundaries, but also for the reservoir. For the fluid part, you need to make some assumptions and to apply the correct boundary conditions. Then I'm going to tell about added mass or added damping in frequency-dependent situations. So what is implemented in DIANA is a so-called coupled equation using an Eulerian pressure formulation. This is a coupling between, say, the displacement of your structure, the dam here, and the potentials, say the dynamic pressures here in the reservoir, the blue part. And what you will actually see that there will be a reduction in the number of degrees of freedom, because we are not solving at the same time, say, the structural part and the flow part, the fluid part in one go. What we will do is that we going to introduce a sort of equivalent element here, which represent the entire reservoir, the entire fluid, and then perform a structural kind of analysis, but on the interface with the fluid and the structure, there will be a mass and damping contribution from the fluid part. As you can see here in this example, someone pointed out in an earlier presentation from that the mesh of the fluid is not matching with the mesh of the solid. That's because in this example there is only a fluid structure interface placed here between the fluid and the dam at the reservoir bottom and the reservoir itself. There is no physical interaction there can be appropriate boundary conditions at the fluid and at the structural domain to account for that. But in this case, the only part where the real fluid structure interaction is taking place is between the reservoir and this vertical side of the dam. What is typical in this kind of fluid structure analysis with this mixed displacement scalar potential approach is that you have small fluid motion. So this is not working if your fluid is in motion, so it will not work, say for instance, for sloshing in tanks. At least it can do it until a limited degree, but what we expect is that there are small displacement amplitudes, small velocity magnitudes, there is a low level of fluid compressibility, so not much change in densities, it is inviscid, and there are no body forces in the fluid domain. So what we have here is we have our structure, this is gamma of omega s, this is the solid domain. You have your fluid domain, this is your omega f. On the interaction between the solid and the fluid, there is the fluid structure interface, this is the gamma I. Then you have a free surface, let's say the fluid top level, that is indicated with the gamma s. Then we also in the fluid we have to take account of about the far field. The infinite extent is sometimes called for the fluid part with gamma E. And at the bottom there can be a prescribed pressure boundary, gamma P, or there can be a bottom absorption effect with gamma B. Added mass. If you do, for instance, a transient analysis, then you will have an added mass contribution of your fluid. This will happen in case of incompressible fluids, and the boundary conditions is that there are no dynamic pressures at the free surface, there are no dynamic pressures at the far field, and there is a full reflective bottom. In the equations of motions, what we then will get is we get the mass of the structure plus the added mass of the fluid. So that's actually not the entire mass of the reservoir that you have modeled, or the fluid part that you modeled, but it's only the part that is dynamically adding mass to the equation of motion. So that can be just a few meters of water from your dam, and the amount of mass from the fluid is being calculated with this method. So you must make sure, of course, that the fluid part that you model is large enough to take into account all the fluid that is in movement. What you see often is, for instance, that the length of the reservoir at the dam is, for instance, 5 to 10 times the height of the dam itself, to make sure that you have enough fluid mass modeled. And what you then will see is you have only added mass, so your mass is now your structured mass plus the added mass from the fluid. And then you still have only structural damping, there's no fluid damping, and you have in a linear way your stiffness from the structure, or in non-linear way you have your internal forces. If we have a frequency dependent added mass and added damping, which is for instance the case when you have compressible fluids, or you have first order surface wave, or you have this far field so-called Sommerfeld radiation boundary, or bottom absorption, then you will have both an added mass and an added damping approach. And you see here that the equation of motion is also then directly written in a frequency formulation, because it is frequency dependent. As you can see here, there's the minus omega squared coming and the I omega. So this can only be solved in case of in the frequency domain. So it is not possible in a standard transient dynamic analysis to to account for compressible fluid, because it gives frequency dependent behavior which cannot be handled in a standard transient dynamic analysis, as we also will see later. Now we are coming to the dynamic analysis types that DIANA is offering. We have a free vibration eigenvalue analysis used to determine the eigenvalues and eigenmodes, a response spectrum analysis. Then we have a modal and a direct frequency response analysis, a transient dynamic analysis, time history analysis sometimes called. We have in DIANA a hybrid frequency time domain analysis, which we'll see makes it possible, for instance, to have some frequency dependent behavior in a time history analysis, which makes, for instance, possible for dam analysis that you can do, say, cracking or interface behavior which is nonlinear, which you want to see in the transient dynamic domain, together with compressibility of the fluid, which is a frequency dependent behavior. How this is being done, I will briefly explain in the HFTD method. And then we have a little bit information on dynamic specific output. A free vibration eigenvalue analysis. What we try to solve in the free vibration eigenvalue analysis is the eigenmodes and the eigenfrequencies which are related to this omega squared. So the relation between your stiffness matrix of the structure and your mass matrix of the structure. Or in fluid structure approach, then your mass is the mass from the structure plus your mass from your fluid. The fluid has no stiffness, so the K remains the K of the. From these eigenmodes and eigenvalues, which will be found from this analysis and can be found in the DIANA output file and in your as output results, we also calculate some typical mode and model related numbers as the modal mass, the effective mass, it's the amount of mass that is moving per mode, also as a percentage of the total mass, which is sometimes prescribed by some model code that you need at least as many modes until you have 90% of the mass participating in your analysis. Participation factors are automatically calculated. You can calculate your Rayleigh damping parameters or let the application calculate your Rayleigh damping parameters based on the found eigenfrequencies or preset frequencies and damping ratios. For the fluid structure one, as already said, your mass matrix is extended with the added mass from the fluid. You see some images of how mode shapes can be visualized in this way with a contour plot. This 3 for dam and here for reinforced concrete structure. The next step, which is also making use of these eigen frequencies, is a response spectrum analysis or RSA analysis. The equation of motion here is your mass times your acceleration plus your stiffness times your displacement is minus your mass matrix times your ground motion. This I here is a matrix which will indicate from which degrees of freedom are corresponding to the direction of your earthquake loading, your ground motion, your ground acceleration here. So that is something that is done internally because you give a direction for your ground motion or directions in case you have multiple base excitation loads. The damping, because you see there is no dedicated C matrix here, so you cannot specify, say, for instance, Rayleigh damping because it is not being used in response spectrum analysis in that way. The damping is in the loading spectrum, in your frequency load diagram. If you see this, for instance, in Eurocode 8, these diagrams are for a certain damping ratio, for instance, 3% or 5% of damping. So you know explicit specification of the damping in sense of material properties, but they are accounted for in your frequency load diagram. Further, what can be done in the response spectrum analysis, which of course needs to be done, is that you do your modal superposition. In DIANA we have three rules which are quite commonly used. It's the absolute rule, which is normally overestimating your results, because that would mean that for each mode you say that your maximum amplitude occurs at the same time. Make a simple example. We have two modes. First has an amplitude of 4, second mode has an amplitude of 3. What will happen? The absolute rule says your maximum amplitude will be 4 plus 3 will be 7. People say, yeah, that is normally too much, because not all the modes will occur at the same time, and an alternative is, for instance, the square root of the sum squares. What will happen again with, we have two modes, one with amplitude 4, one with amplitude 3, is we take the square root of 4 squared plus 3 squared is the square root of 25. So the estimated amplitude is not 7 anymore, if you could see in the absolute rule, but will become square root of 25, which will be 5. And in between them there is the so-called complete quadratic combination, which takes into account that for modes that are closely spaced to each other in the sense of frequency, so if eigenfrequencies of modes are close to each other, it's more likely that these amplitudes also going to correspond, occur at the same time. So what they do, they add a correlation coefficient between modes, and if modes are far spaced from each other, the correlation coefficient is nearly 0, which would lead to an SRS kind of solution. And for all the modes that are closely spaced to each other, there will be an absolute superposition rule. So the CQC results are always between the absolute rule and the square root of some squares rules. And depending on your model code and your guidelines, national guidelines, you probably are set to use either CQC or SRSS. The output in DIANA will be, for response spectrum analysis, will be minimum and maximum output results, a sort of envelope. That is because in case you want to add a static load, you're going to shift your amplitude. Say, for instance, we had our amplitude of 5 from this SRSS, but say our pre-stress, our static load gives already -2, which means that the maximum is -2 plus 5 will be, say, 3. And on the compression side, it will be -2 minus 5 will be -7. So in that case, it's not sufficient anymore to only give the amplitude, as in the previous DIANA versions were. But due to these additional static load, which is also in quite many model codes required to take care of this part, we give now a minimum and a maximum envelope of the output results. In case you want to do fluid structure interaction approach, then you again can only do an added mass approach. So you have your MF here, and you have your MF also in your loading. So you do only have an added mass approach. Results will look like here, where you see the SXX for tunnel. This is the H result. It's probably not visible, but so that it means the high result. If you have no static load, your low result is just minus the high result. But when I say if you have some static load, for instance, the self-weight or so, then it will shift your band, and the high and the low will differ in not only in sign but also in value. Here we see, for instance, the reinforcement bar of a reinforced concrete structure, and we see the stresses occurring, the maximum stresses occurring in the reinforcements bar, which can give an indication of where the construction may start yielding or damaging. In a modal frequency response, we again are using the eigenmodes and eigenfrequencies. The equation of motion is written here again. We are talking now about the frequency domain, so this is a frequency formulation. So we have a complex displacement and we have a complex loading, and there is a relation here between your mass matrix and your stiffness matrix. As this looks very familiar indeed as the eigenvalue analysis, and that's exactly what you're using here. You can apply a modal damping, which is taken into account. It's not really, say, visible as a full C matrix here, but it will apply a reduction on your response for the loading depending on the mode. The modal damping can be given either as one value for all the modes, or you can be given as a different ratios for each eigenmode included. Here you can use the frequency load diagrams, complex loading with amplitude and phase and real and imaginary parts possible. The output is also complex for this kind of analysis, which means you can either see it as amplitude and phase angle or as a real and imaginary part of the solution. Sometimes depending on your output device, what is being offered. For instance, in the DIANA output device, we send the result as a complex number, as a real and imaginary part, to the post-processor, but in the post-processor, the post-processor itself calculates the amplitude and the phase angle. For other output devices, for instance, just tabulated output, you can choose yourself whether you want amplitude and phase angle or real and imaginary part. In case of the fluid structure interaction, if you want to do modal frequency response analysis, you are limited only to an added mass approach. You cannot do added damping because that doesn't fit in the eigenmode calculation. If you want to do that, we will come to the direct frequency response analysis, because what you see here, there is your real damping matrix. So if you have structural dampers or continuous damping involved, you want to calculate in the frequency domain, you need to go to a direct frequency response analysis. Also here the same story about the loading and the output. It's complex. What is important is when you compare a direct frequency response analysis to a modal frequency response analysis in sense of calculation time, then the direct frequency response analysis needs much more calculation time. That is because this complex equation needs to be solved for each excitation frequency omega. While in the modal damping, of the modal frequency response analysis, where you are limited to the modal damping, you only calculate your eigenfrequencies and your eigenmodes once, and then you can calculate the response from that, which is much faster than for each excitation frequency solving this complex equation of motion. So when you have no viscous, structural or continuous damping, and you say have enough with modal damping, then you can use the modal frequency response analysis. It will be more efficient in time than direct frequency response analysis. In case you have this damping, or for instance in the fluid the compressibility, then you are more or less forced in the frequency domain to do a full direct frequency response analysis to account both for the added mass and the added damping. Results, it's the same as for the modal frequency analysis, will be presented in the frequency domain as, in this case, a nodal acceleration, and here you see the typical at the eigenfrequencies, you will see the spikes coming back for this 5-story building. In the transient dynamic analysis, we're talking now, we're back to the time domain, of time history as it's often called. We have our equations of motions. can be linear or non-linear. In DIANA, you, for both cases, use the star non-lin command, even if you are just using linear elastic material, but you want to do time steps, you're using star non-lin. That doesn't make any difference because the system will, if you set it up correctly, it will see that it is that you do a linear analysis and you will not be harmed by any non-linear material, for instance. And the commands are the same. The material properties are only different. You can use viscous Rayleigh damping. You can use discrete dampers. It is possible to update your Rayleigh damping, which you've seen. C is alpha times the mass matrix, which is beta times the stiffness matrix, to do beta times the tangent stiffness matrix. So each step, if your matrix is changing due to hardening or softening or cracking, or then you can also update your C matrix accordingly. If you don't switch on that option, then the damping matrix is set up only once based on the initial on the mass matrix and the initial linear elastic stiffness matrix. But it's possible to let that update each step. It is possible, in case you want to use relative displacement, to do a correction, because there is a small difference whether you use say a total displacement formulation or a relative displacement formulation, and that can be compensated in case you want to do relative displacement instead of the total. If you want to compare it, for instance, with a package that is doing a relative displacement, then these damping matrix, these damping contribution need to be corrected because there is the KU and the MU dot involved. For details about this, I refer to the DIANA documentation, and there is an example where this correction is explained in detail. The next thing that you can do in a transient dynamic analysis is that you also apply geometric nonlinearities next to, say, physical nonlinearities. It is also work to use ambient time, to include ambient time dependencies, say temperature or concentrations, pressures. The loading is provided as the time load diagrams in combination with for instance, base excitations or acceleration, but it's also possible just to apply this time load diagram to standard loads like forces, moments, or prescribed displacements. So you're not limited to accelerations. You can use all kind of loading that you have available in the standard nonlinear static analysis as well. You can just attach a time curve, time load curve to that for most of the loads. What will happen in fluid structure interaction is you can do the added mass again, so your mass of your structure is extended with the mass of the reservoir. In DIANA, we use in this transient dynamic analysis, in any transient analysis, so even if you don't want to account for the mass terms, but only want to take into account velocity effects, we use implicit time integration schemes. Implicit means that the solution at, say, your next time step, the time you're going to calculate, is based on the equation of motion of that time step. So you actually solve your mass times your next acceleration plus your damping times your next velocity, the velocity of your next step, plus your internal forces of the next step and the external forces. While explicit methods use the equation of motion of the current time to make a prediction for the next time. Therefore, in DIANA, we choose to go for the implicit time integration. We have several methods available: Euler backward, first order accurate and stable, which means compared to the Newmark, which is second order accurate, that a solution with a Newmark, Hilbert, Taylor, Wilson, or the Runge-Kutta method is more accurate. What in practice mean is that an Euler backward, which is the fastest method, to achieve the same accuracy as the other methods, you will need much smaller time steps, and then the benefit of doing, say, the fast Euler backward method is lost due to the required smaller step sizes to get to the same accuracy in the solution. So yes, Euler backward is the fastest, but due to the accuracy and the need and that way the smaller time steps needed, the methods do not matter so much. The nice thing about the default Newmark method that it's unconditionally stable, which means that for all the time steps you choose, it is stable, while in the Euler backward, the time step is stable as long as you met certain conditions. Hilbert-Hughes-Taylor is actually similar to Newmark, except with slightly different values in the equation set, which makes that the Hilbert-Hughes-Taylor introduces some numerical damping for higher frequencies, which is sometimes wanted to avoid some spurious modes, which you sometimes see occurring in calculations. Wilson is another variant, and the Runge-Kutta is another variant. For details of this time integration methods, please look into the analysis procedures manual, where the differences between the methods are explained. In general, the implicit time integration method can use larger time steps than explicit methods because we are really solving the equation at the current time point of interest. You can use in this transient dynamic analysis consistent or lumped mass and damping matrices. You can also use the linear and quadratic elements as you use. And we would like to know from you, what are you using? Are you using implicit or are you using explicit methods? So please fill out our poll. Thanks for the people that were willing to give information of what methods they are currently using. We see roughly that 2/3 of you, at least of the participants who answered the question, are using implicit methods, and 1/3 is using explicit methods. In the end, both methods should come to the same solution, so it's not said that one method is superior to other methods. But the thing is, in case of the solution and convergence, it sometimes is easier to solve the real equation of motion. Sometimes in explicit methods, a solution can be found based on the current matrices, the current step, but the question is whether it always will also completely match the equation of motion at the actual time. So that's why in DIANA we prefer to solve the equation of motion really at the next time step. But as I said, the method, any method here is the same for what kind of methods. In the end, you should come to the same solution. The way you do it should not matter. What we have seen earlier with respect to the element size and waves also applies to the time steps. To be able to see for a certain point the response correctly is that you need sufficiently small time steps to really represent the response. what would happen if we did not choose, say, 20 time steps, but we use just 2 time steps, which will mean we will find at 10 we will find 0, and at 20 we will find 0 again. It would give the indication that there is no wave occurring at all. So we need to have our time steps sufficiently small to nicely see the response at a certain point in time. And also here we have as a guideline, we want to use at least 20 time steps to represent one period of a motion. So the wave period time, this is t minus, the smallest one we want to see, is related to the maximum frequency you want to see. So for instance, again, if we want to see a maximum frequency of 50 Hertz, which means that the smallest period time of the waves we can see is 0.02 seconds, which means that we would need time steps of 1,000th of a second. Of course, you can say, I say 10 steps is enough. Okay, you can go up a little bit, but this is a guideline. It gives you information from the maximum frequencies you want to see related to your time steps. I want to shortly show here a project we did last year, or it started already in 2013. It's a benchmark. It's a 1.4 scale of a nuclear part of a nuclear building. It's been placed on a shaking table. It is fully instrumented with all kind of measurements. And well, this experiment was compared with numerical models. For the DIANA model, we choose to model the shaking table and the reinforced concrete structure. The reinforced concrete structure is modeled with solid elements with nearly 1,300 reinforcement bars. The shaking table is modeled with curved shell elements, and there were four actuators horizontally and 4 vertically, and all the loading is prescribed, and the same experiments of the same loading is applied to the numerical models as on the experimental model. And for one of these runs, we show the DIANA results compared to the experimental results. For instance, in this corner point, and you see that we were able to match the numerical of the experimental results quite well. On these pictures, also results from the transient dynamic analysis. You can see the maximum crack width as experienced until that point. You can see that this wall is heavily damaged. Later this year, we will have a dedicated webinar on this model where we go into much more detail about how such a model is being set up, where we also take into account the choice of the material properties and the reinforcement properties. Also nice related to the dynamics is a static pushover analysis and a response spectrum analysis that is performed on this model, and we can go in much more detail, but this is just here to show from what is possible to see from a transient dynamic analysis. So you can see things like showing your time history, but you can also give nice plots about the damage experienced during such seismic loading. A special type of analysis is the hybrid frequency time domain analysis. What you see here in the equation of motion is that we have, in case of the fluid structure interaction, because this model is built for fluid structure interaction, for analysis of dams, that we can have both the added mass and the added damping of the fluid. And you will also see this occurring in your right hand side. And you see here a a special load. This Q load is so-called pseudo force, which will be taken into account into the frequency domain, and it's is representing the nonlinear effects which occur in the time domain. These are transferred from the time domain to the frequency domain, and this equation is solved in an iterative way until the point that our pseudo force is becoming stable, which means that our nonlinear forces are being fully covered by this pseudo force in the frequency domain. In this way, it is possible to do an added mass and added damping approach for fluid structure interaction. The loading is limited to base excitations. These are given in the time domain as accelerograms, but internally we are using Fourier transforms to transfer them for the time from the time to the frequency domain and back to do this iterative process. It requires that your time load diagrams have equidistant time steps because that's needed for the Fourier transforms and inverse Fourier transforms needed. The nice thing in this hybrid frequency time domain analysis that we also make use of generalized coordinates. We make use of the mode shapes of the structure to reduce the degrees of freedom. Imagine you have your model of a dam, or maybe even a large structural model only, and you don't want to do a full transient dynamic analysis because, yeah, with these small time steps, it will take a lot of time. So what we do, we use the mode shapes. So instead of, say, the 100,000 degrees of freedom, we are going to use 50 modes or 100 modes, and we can solve this equation for just, say, 50 degrees of freedom, making use of the mode shapes. This is also then the limitation about this hybrid frequency time domain analysis. The nonlinearities you can take into account must be local, which means that the mode shapes are not going to change during the analysis because it is used on these mode shapes. So you can imagine if you have so much damage that the mode shape is not matching anymore, then this whole equation of motion is not valid anymore, and your solution is also worthless. So, but in case you have, say, local cracks or local interface behavior with this hybrid frequency time domain analysis, you can resolve it. You can take, for instance, compressibility and first order surface waves of the fluid into account. Or if you only want to do a structural analysis, but don't want to do but want to use your mode shapes because you're mainly doing nearly linear elastic kind of analysis, you can also use the hybrid frequency time domain method. Your pseudo force will then remain small, so that means you don't need many iterations, but you can still use the benefit or using this generalized coordinate, the mode shapes. So non-linearity is allowed. You can use the viscous and Rayleigh damping. What you need to take into account, because we are switching from the solution in the frequency domain for the steady state solution to the time domain, we need to have sufficient damping to meet the initial conditions. In case you don't have any damping and we calculate this steady state solution, it will look in the time as if your structure is already moving before your loading has started. That's because you calculated the solution in the frequency domain. And when using sufficient damping, you can still match these nice initial conditions. What you can also see here, if you just calculate, say, a dam, so that we take the displacement here at the top of the dam, and you do just an incompressible calculation, then you will see exactly the same time history if you would have done a nonlinear transient dynamic analysis. But if you want to take into account compressibility and bottom absorption and radiation boundaries, you see that you have more energy dissipation and your peaks, your maximum displacement will be much lower. Then we are going to end this presentation with some dynamic specific output items. These are for the transient and dynamic analysis, the relative total and relative displacements. The frequency analysis only gives relative displacements. Velocities, accelerations can be seen. It is possible to calculate the element inertia forces and moments, the damping forces and moment, and for fluid structure interactions also possible to display the dynamic pressures, as you can see, for instance, in the example here to the right. In a transient dynamic analysis and an HFTD analysis, it's possible to ask for extreme results. So over all your time steps, you can see your maximum and minimum displacements or stresses or whatever result item of interest. Selections can be made dependent on the analysis type, can be based on the time steps, your modes, or your excitation frequencies. And this ends my presentation, so I'm going to hand it over to Maziar. We are willing to answer some questions shortly.